Hi, good evening, and welcome to the ZP Developer Zone. So it's classic, the date is always one day wrong, but we always intend to do these on the Sunday. But then again, Saturday nights can be a little bit freer. There's not many people wanting meetings, etc. So Saturday night's also a good time to do a ZP Developer Zone. With that said, let me jump into it and just sort of say that we, of course, we try to answer questions of a technical nature that are coming during the week. And that's what I'm going to jump into doing. Just to kind of say that, well, there'll be some links to ZP technology. There's only 5 days left in January, but here's a discount code for January. So if you see any ZP technologies that look interesting, you can click various links that I'll put underneath the video and use that discount code, and you can get 10% off. With that said, let me go through the questions for this week. This was a good one. This was sweet. Somebody, apparently this question originally came from the YouTube comments, and then the team said reach out to ZP and the team will answer it. So the question here is, why are differential pulse voltammetry peaks larger than cyclic voltammetry peaks? Let me give you a demonstration. So in fact, I just want to say this is not all going to be talk this evening. I've got sensors in front of me, I've got solutions in front of me, I've got pipettes in front of me, I've got Potentiostat in front of me. So we'll be doing some, let's say, real science as well. I think that's what makes the ZP Developer Zone a little bit different, that we do actually do science as well whilst doing this. So we will talk about DPV, Differential Pulse Voltammetry, and we'll also talk about Cyclic Voltammetry as well this evening. Also, the Sensi All. Appreciate the people who are now buying the Sensi All Potentiostat. This is the Sensi All Potentiostat. I have had some user feedback this week. The good news is we've actually implemented some of the feedback already, and I am going to answer some of those questions this evening, and also to say we're going to have some more updates as well. So the nice thing about this is a really modern form of potentiostat. So when somebody makes a suggestion and it's actually, and it's a good suggestion, no firmware updates, nothing funny like that. This is a cloud-enabled potentiostat. We're able to just roll out those updates straight away. So a very powerful 2025 technology. So I appreciate the feedback. I'll go through it. pH sensors for IVF, in vitro fertilization. Somebody's probably just interested in the form factor of our sensors. So if I just kind of hold up a kind of ZP type sensor, this is what they look like. They probably work quite well. They work very well in IVD, in vitro diagnostics. So, measuring small solutions that you may get, for example, in IVF, in vitro fertilization. We've probably got the right kind of form factor for that. This is a bit of an ongoing question. Somebody asked us a question about rectangular versus circular electrodes. They also gave me some feedback as well, because I kind of said, you know what, it doesn't really matter whether it's circular or rectangular. Now this evening I'll show you sometimes why they are rectangular and sometimes why they're circular. They were also asking, how do I modify an electrode? So I do have an old video on that, so I'll be linking to some previous material. And then just lastly, somebody wants to build a Severinghaus electrode. I will discuss it. They want to make a solid state Severinghaus electrode, so I will also link to the right pH sensors for doing that as well. So question number one is about the question they're kind of asking originally on YouTube, but then it kind of came into our Contact Us page as well. Why are differential pulse voltammetry peaks bigger than cyclic voltammetry peaks? So that's the kind of question I'm going to ask. Not ask, rather answer. I think I've got here the word demo. So let me just dive in and do a quick demonstration. Let's say. So I've got a screen printed electrode here. I've got some ferricyanide, 5 millimolar ferricyanide solution here. Let me just grab some solution. Now, I sort of talk a lot when I'm doing this because I'm just trying to remind myself what stage I'm at when doing this. So let me just put the solution on like that. And let me just go. I want to bring up cyclic voltammetry. So the first part of that question was actually about cyclic voltammetry. Well, actually, the first part of the question was actually about square wave voltammetry. Oh, no, sorry. No, not. Well, in fact, I've hit square wave voltammetry. I just want to say that square wave voltammetry and differential pulse voltammetry, I know they have different waveforms, but they're really quite similar, actually. And so, personally, I prefer square wave voltammetry. So let me do square wave voltammetry, but I just want to do a demonstration. I know your question is why a DPV, differential pulse voltammetry, peaks higher than cyclic voltammetry peaks. Let me start off by actually doing square wave voltammetry, which I have here. I'm just going to name this file because I want to be able to find it later on. This is ferricyanide, badly spelt. Ferry, SQV, done. Right. Now I'm about ready to go, but I just want to kind of put in some, I'll put my start potential as minus 200 millivolts. I'll put my stop potential as 600 millivolts. My step potential as 1 millivolt. My current range as probably 100 microamps. My 100 microamps. Yeah. My amplitude as 40 millivolts, and then my frequency as 30 hertz. Now, just out of interest, I got some feedback from one of our users that said this is a little bit sensitive. Now, you saw how quickly I just did that. So we took their feedback and we've reduced the sensitivity of these settings. So if you're a user of this Sensi-All platform, you know, and you give us some feedback, it's really super quick to kind of, you know, take on that feedback. So it's not like they even have to do a firmware update or anything like that. We just changed it in the cloud. So I'm just going to hit hopefully start measurement, and off it goes. So I'm going to do square wave voltammetry and minus 200. So hopefully that will, and it'll upload. And I say hopefully it will upload now. I'm just going to, when it says upload complete, which is what it's now said, that means that the data has actually gone to a cloud system called Julie, and we're able to go online and basically grab the data. So I'll just navigating to it now, which is what I'm doing, and I will, good. And where are you? You are here, right? Okay, so I shall share the screen with you really quick. Yeah, here we go. I need to. All right, cool. Right, so what I can do here then is I can actually see my data, and I can then see the square wave voltammetry. And so square wave and differential pulse voltammetry actually behave very similarly, and you know, you can sort of see a very clean kind of peak, which is really kind of, you know, warming, if I can put it that way. You know, that you get this nice kind of, here I'm looking at the oxidation of ferricyanide. Now I know it's ferrocyanide rather to ferricyanide. Now I know that I said, well, I put ferricyanide on it. So you could ask yourself, well, how am I oxidizing ferrocyanide to ferricyanide? Well, I started at minus 200 millivolts. So in fact, I created the ferrocyanide in situ. But you can see what a kind of nice peak I get. Now, I know your question is differential pulse voltammetry, but the Sensi-All platform, and I'm going to do a demo and then I'll talk about the theory. The platform does square wave voltammetry, not differential pulse voltammetry. It's my opinion, but they're so close. Square wave voltammetry, you know, is just sort of, I don't know, for some reason over recent years in literature, it's kind of slightly won out over over differential pulse voltammetry rather. Now what I want to do is go back to here and bring up, in fact, the app again. I'm just going to go to Cyclic Voltammetry, which I will do. Whoops a daisy, there we go. Yep, Cyclic Voltammetry. I will just call this CV so I can find it again. CV. I will go here. I will go continue. I'll start at minus 200 millivolts, go to 600 millivolts, 100 millivolts. I just want to do scan rate. I want to do it quite quickly. I'll just bring that up, that current range up a little bit. And I think I'm in good shape, and off we go. So I get a little peak for the ferricyanide, and then it'll kind of reverse, and then we'll get essentially the reduction, and then it's only once. Oh, I've done 3 cycles. Okay, so it's a bit boring because I've actually done 3 cycles. But the questioner is asking, why do you get more intense or higher peaks for differential pulse voltammetry as opposed to cyclic voltammetry? Now, I know I'm doing square wave voltammetry, but square wave voltammetry and differential pulse voltammetry are quite similar. So it's just running the cyclic voltammetry. Now, when it's got to the end, it'll upload the data. I'll have a quick look at it, and we can essentially discuss what we're looking at that point. Right, up it goes. Right, upload complete. Cool. All right, so upload complete means that it's gone to Julie. Everyone who's got a Sense It All, you're entitled to what we call a Premier account in Julie. So I'm just gonna log in now. I can see the data here. I'll just zoom in. In fact, I'll just zoom in slightly and have a look at it. So when you look at this, I agree that the peak heights look better in square wave voltammetry. Whether they're always consistently higher magnitude, that I'm not sure I agree with, but they look more intense. Now I'm going to talk about why do square wave and differential pulse voltammetry peaks look more intense than cyclic voltammetry. So let me go back to the presentation. Now that Sense It All, you saw that I was actually able to do a quick demonstration on that platform, really no problems. And let's just, now the first thing to say is when you're doing cyclic voltammetry and linear sweep voltammetry, I know you know this because you wouldn't have watched our videos online, but what we're doing is we're basically, historically potentiostats would have done a linear change in potential with time, but we live in a digital world now, and actually most electrodes are digital. So that means that we're sort of stepping the potential in little steps, stepping the potential in little steps, stepping the potential in little steps. So that's what linear sweep voltammetry is doing. And then what we're doing is we're sampling these current steps. So the current is being essentially spiked up with each little potential step, and we're sampling at the back end of it, and that's leading to what you perceive as the kind of current versus potential. But in fact, you could argue that this is actually filtered as a function of time, because we don't just gather all of the current here. We're actually just filtering on the back end of the spike. Now that current that we're plotting has 2 components, and I know that the guy who's asking the question, or the person who's asking the question, knows this because they would have watched other videos. But that current contains 2 contributions: the Faradaic current. In this particular case, we were oxidizing, because I started at a negative potential. We'd basically generated ferrocyanide, and we were looking at the oxidation of ferrocyanide into ferricyanide. So we were looking at 2 components there: the Faradaic process, which is the oxidation of ferrocyanide into ferricyanide, and then a background non-Faradaic component, which they kind of call, you can call it the capacitance current. And they say, and I agree, square wave voltammetry and differential pulse voltammetry are really good at subtracting that background current because they have a more unusual waveform. And I think you can see it in the data. In fact, you can see that is an oxidation peak, but it's kind of it looks a little bit distorted, if I can say. It's not so clear. But of course, when we did the differential pulse voltammetry there, or actually we did square wave, but they are very similar. It's got a different waveform where, in fact, we kind of got this not just stepping potential, but we step up, we step down, we step up, we step down. And in fact, we sample, and when we get these spiking currents for each one, and we sample here, and then we also get when we step down here, we also get a spiking current, and we sample here. And what we're actually ending up doing is we're actually not looking at the current straight away. We're actually looking at a differential current between what we call the forward and the reverse. And this is said to, and my at least experience is telling me that this works quite well. In fact, that experiment I just did sort of showed it, that what's happening here is that we're getting a whole bunch of forwards and a whole bunch of reverses. And if we then plot these out, we get a forward, we get a reverse, and then you get when you do the difference between those 2, you get a very nice Faradaic only signal. So what you're meant to be doing with square wave voltammetry, differential pulse voltammetry, is you're able to subtract rather the background signal, and you end up with a good looking peak. And in fact, that data was actually really quite good looking, you know, and good looking is a very strange term, I know, but it was quite clear, you know, that that was a redox peak as opposed to cyclic voltammetry, where you're quite distorted. And also I think it's, you know, it does a good job of, yeah, it does basically does a good job of subtracting components of the current that are not Faradaic. So we're left really just with the oxidation of ferrocyanide to ferricyanide. So at Zimmer and Peacock, a lot of the time these days, if we're doing functionalization of sensors and characterization of sensors, we may use cyclic voltammetry, quick and easy. But if we're doing analytical work, measuring that analyte, then we will often use square wave voltammetry. And the nice thing about the Potentiostat is it can do amperometry, open circuit potentiometry, EIS, linear sweep, cyclic voltammetry, square wave voltammetry. Now, if you're still got questions about this, we can return to this, but I do have, unfortunately, another sort of 4-ish questions to go through, so I might have to kind of skip forward a little bit on this. As I say, we're quite big fans at square wave voltammetry at ZP. Now, Sense It All Potentiostat, very much appreciate people being clients and customers of the Sense It All Potentiostat. Somebody was asking us at the beginning of the week, or maybe, beginning of the week, you know, they were trying to set the settings in on the Potentiostat. Now, you saw how quickly I did it this evening, because we took their feedback and we went back and we said, okay, maybe we need to decrease the sensitivity a little bit. So in fact, we have enabled it to be, let's say, more accurate. So how can I illustrate that? So I got some cyclic voltammetry, when I say more accurate, more easy to set. So if I just go continue, if I want to start the potential at 950, easy enough, 850, you know, 650. Let me just make up, I want to go to 700. 700. Let's say I want to start potential at minus 500. Minus 500. So we can let people use it. If they want us to, you know, decrease the sensitivity a little bit more, we can do it. Again, it's really sweet because actually we can do these improvements essentially in our cloud, and actually then you can get the benefits. So it's not even like we even ask people to update the app or anything like that. It's really quite a sweet little system. So we do take your feedback and we are improving it. They were asking whether it was compatible with tablets. So if you can navigate to a device and see the app on either the Google Play Store or the Apple App Store, then it is compatible with that device. So to make the point, I did take, in fact, it's probably kicking around here somewhere. I did take an old iPad this evening, and actually, I did install the app on the iPad, and I was actually able to run it on the iPad. Now, I know, you know, we obviously advertise it as the case, but I did have made sure I did a little confirmation this evening to make sure that we could run this on the iPad, and of course it does run. So, iOS, Android. If you want to know whether you can use a particular iPad, etc., obviously all modern ones will work. And the one I was using was an older one, but I navigated to the App Store. I could see the app, and therefore I could actually download it. I was a little confused by this because they were asking about electrode adapters. The Sense It All Potentiostat is ideally set up to work with the ZP screen printed electrodes in this kind of format. Now, there's a real benefit to that, actually. And in fact, the benefit, I've got to do another demonstration in a bit. So let me take that sensor. Easy to take out. Let me put this sensor in. Here it is. Look at the way it's designed, so I don't have to touch that. And then I can just put it in like that. This is keyed, so it just slots in like that. And listen to this. Just clicks in like that. I was watching a video the other day where... in fact, I might just grab something quickly. I was watching a video the other day where somebody, you know, this is an old ZP product, and this is where we learned our lesson. Here's a screen printed electrode. I'm already touching the end of where I'm actually going to add the chemistry, so I'm already contaminating this because there's nowhere else to grab it. And then I've got to slot it in here, and look, it's springs around. Absolute. For the thing about Zimmer and Peacock is that we're really trying to get people to actually market and to have impact. So when you're trying to take assays out of your lab and into the real world, asking people to slot, and these are DP products, by the way, so we've learned our lesson. You know, that is not an easy thing to slot, actually. And that's a big problem with many of these kind of small potentiostats. With this one, it is designed to work with these adapters. It does a really good job. And this potentiostat has a different life to it. It's meant to be an R&D tool, and it's meant to get assays out of the lab. So unfortunately, they work best with our, I would call this a new generation, actually, of screen printed electrodes. And I think something that's really not thought about a lot is the user experience. You know, we think of these as R&D tools, but we think of these as actually MVP, minimally viable products, for getting assays out of the lab. So they are designed to work with these kind of adapters that we've got. And it won't perform necessarily well unless you're using the adapter. We are we on our website, by the way, we do have design rules. If people want to use these kind of adapters, we do have design rules so they can actually follow our design rules and make their own screen printed electrodes for this. This person brought up a really good point, and it's something I'm doing, that when I do a method, it's always good to have a record of the method. So when I say do a method, I should turn this on, for example. Here, I've got all the settings. So we're working on it now that those settings will get saved in the cloud as well, so that you've got a permanent record of the settings. So you don't have to make any changes. We can just implement that. And then this is a really good point as well, actually, and I really appreciated that. They wanted to be able to... What's really good about this potentiostat is I do measurements, the time, the date, and who did it is all saved in the cloud. Fantastic. But it's using what's called, I think, UTC, Universal Time, maybe coordination, the C stands for. So it's using the world clock, if I can put it that way. And so I'm going to talk to the engineers and actually make it so you can set your time zone in your account so that it can be in your local time zone. So good feedback. It's cloud system, so actually we can do these kind of improvements. I'm just showing you here that actually I did find the Sense It All app on the Apple App Store. I was able to install it. When you install it, you have to let it use the Bluetooth, and you also have to let it use your camera. And after that, then I was able to get the app on the iPad as well. So in answering the question, I went and did it, make sure that that is still operational. Somebody wants to measure the pH of IVF, in vitro fertilization. I say here, so this is the pH sensor that at Zimmer and Peacock, we sell biosensors. Now, these biosensors we sell on our web store are only really to get to TRL3, Technology Readiness Level number 3. Technology Readiness Level number 3 is just go in the lab, do a proof of principle. They're not designed that you can then go in and put them into a medical system. We are ISO 13485. We are qualified and certified to do contract development, contract manufacturing. People can do their own experiments and prove out a principle by buying things off our web store, but that then doesn't give you license to go and put it into a medical product. You've got to do a massive risk assessment on this kind of stuff. But that said, if somebody came to me and said, well, I just want to try out whether I can do this in principle, then I've put a link here. I've put which button to click. And when you click that button, you'll come to a particular pH sensor. And I think I'll just do a quick demonstration actually now of how I think this kind of experiment would play out if I was going to do a proof of principle. So in fact, let me pull... I use my own technology when criticizing old designs that we had. So I'll move that out of the way. This is now what we have. It's a really kind of a beautiful thing. Let me just go into a slightly different mode. Amperometry, I don't want amperometry. I want not AIS. Open circuit potentiometry. All right, cool. This is OCP. I'll call it OCP 101. Right, and I'm just thinking aloud to myself. Continue. Right, so I'm almost ready to go. I'm just going to put a solution onto this. This is kind of, if I was trying to prove out that I could measure the pH in an IVF solution. I can kind of imagine the experiment, so I may I'll put a solution on here, which I have done. As I say, we've really improved now. Now I'm going to do this one for 30 seconds, but I just want to kind of, you know, if I wanted to do this for let's say 60 seconds. 60 seconds is easy enough to set up as well. In fact, I will do it for 60 seconds. What I'm going to now do is I'm going to start the measurement. I must have not done it for 60 seconds. I must have done it for 30 seconds. Start the measurement. When it gets to about 15 seconds, I'll change the pH. Coming up now. Right, now I'll just change the pH. Now what I'm demonstrating here is the ability to actually measure quite small solutions and be able to measure the changes in those solutions. You can see that as I add material, I can change the signal quite considerably. And so that's the kind of experiment I would do to kind of demonstrate that I can actually measure something like an IVF solution. And now you can see it settling to that new baseline. And what I will do is have a quick look at that. So I just wanted to kind of demonstrate that we can do things like measuring the pH of small solutions. Now this is a question. So the question kind of came in last week. I answered it, and then some further questions came in. So last week we discussed people think it's really important whether something's rectangular or circular. It's not the electrochemistry that really determines whether you want whether you want rectangular or circular. It's actually more complicated than just that. It's a shocking statement actually, and that it ain't all about the electrochemistry. There's more reasons why. Now I quite like circular because actually circular allows you to just pipette on, and it's easy to functionalize. Now there'll be a third slide where I talk about when rectangular can actually be a real advantage. Now they are asking, how do I functionalize and I presume a carbon electrode. I'm a big fan of carbon electrodes because just of the cost, and I have done quite detailed videos about how to functionalize carbon electrodes for making things like antibodies, etc. So there's a whole sort of video about that. If you see a link, then that means I've also linked to it underneath. I'll also put a link underneath this video as well. Just FYI, sometimes why you would choose a rectangular electrode rather than a circular electrode. This is a good example of why we originally started with a rectangular electrode. I think ZP is really one of the few manufacturers of screw-fitted electrodes, especially in the R&D market, that have genuinely made medical devices. I started my career in 2000 making glucose strips. And in a glucose strip, they have what's called self-filling. Not self-filling. Essentially, assay starts as soon as the solution kind of comes in. So we know that in part, an SPE, maybe a screen-printed electrode, may end up in a microfluidic device. And a blood glucose strip is a kind of classic of that. And so we've designed our electrodes so that when that drop of blood kind of goes in there, it will start wicking in there, and when it actually is wicked in, it covers all the electrode, and then we can start the assay automatically. So sometimes the designs are not for the electrochemistry, they're actually forming a different function here, which is actually the automatic start of a glucose assay, for example. Now question number 5, somebody wants to build a solid state. I think there's a bit of a spelling mistake in here. Severinghaus electrode. I must have to check that spelling, whether the E is there or not. But that said, it's a way of measuring carbon dioxide. So what's wrong with these electrodes often is that they're quite, they got electrolyte in them, they're quite bulky. But at ZP, we're really good at reducing large steel-bodied electrodes or glass-barreled electrodes down to something that's a lot more solid state. The Severinghaus electrode works on the principle that carbon dioxide can get across a membrane. It dissolves into an electrolyte, and that causes a potential change. And you can sort of detect the carbon dioxide because actually it forms carbonic acid, and carbonic acid dissociates and gives you pH. We do have pH electrodes, and I have talked about this in 2022. I think I may, and I'm sort of saying that you take one of our hypervalue pH electrodes, which I will link to in a minute. It's already got the reference electrode built in, so that's kind of taken care of. And then you would put a membrane over here that would give you some permeability to carbon dioxide, but would exclude other materials. And that's how I would start creating a solid state Severinghaus electrode. And I've linked here to the pH sensor that I would actually recommend for this application. I've also linked here to the electronics that you could use to do this. Either our sensor or Potentiostat, which obviously I'm biased and we would want you to use, or you can also use our single purpose biosensor circuit as well. So question number 1. Differential pulse voltammetry is not so much taller or more signal than cyclic voltammetry. It's just a cleaner signal because it's very good at subtracting those current components that are not Faradaic. So we got a very nice oxidation peak for ferrocyanide to ferricyanide, because in fact I use square wave voltammetry, so I didn't use differential pulse, but they're very similar. It was very good at subtracting the background. So square wave, differential pulse, they both work, and they both give you a better signal than cyclic voltammetry, because cyclic voltammetry has a Faradaic and non-Faradaic component about it. Thank you for the feedback on the sensor or Potentiostat. We've already implemented some of what you've given us, and we'll implement the rest. This is a complete cloud system, so in fact we can implement improvement, and you wouldn't even have to update the app. It's a really kind of cool system like that. I did a small pH measurement experiment because I'm just kind of saying that I think for IVF, in fact, we do have a technology platform that's really good for it, for measuring pH. But you can, if somebody chooses to do this, the components that we have on the website will only be good for proof of principle, TRL3, technology readiness level number 3 in the lab. Don't buy our pH sensors thinking that you're going to go and put them into a medical application. You really have to engage with ZP, because we're ISO 13485. You've got to do a proper risk assessment, etc. You're building a medical device. You can't just buy stuff off web stores and put them into medical devices. I do have videos on how to form an immunoassay on top of those electrodes, and I will have linked to that underneath this video. I'm building all Severinghaus electrodes. You would use our hypervalue pH electrode and just put a carbon dioxide permeable membrane over the top of it, and that would help you measure the carbon dioxide, because the carbon dioxide would form carbonic acid. The carbonic acid would dissociate, that would give you the pH, and that would be the source of your signal. If you have any technical questions regarding electrochemical biosensors, electroassays, you can see we've covered it all this evening. Don't hesitate to reach out to us. Okay, thanks very much.